Hello and welcome back to Introduction to Algorithms. Today we're going to start chapter 1 about Introduction to Algorithms. So here you see the slides, and I want to convey to you the gist of computational problems and their algorithmic solution. So we're going to talk about the power of abstraction that I mentioned already in the initial part, ignoring certain aspects to be filled in later or to be filled in advance, and thus can be built on when higher levels of abstraction. We talk about the so-called virtues of computer science, the essence, what makes of the difference between computer science and electrical engineering, because at the end, both kind of deal, scientific areas deal with computing technology, right? These kind of virtues are specification. First, unambiguously agree on what computational problem is to be solved. Then algorithm design as opposed to coding, algorithm analysis, which involves correctness and asymptotic cost, as opposed to, for example, empirical runtime measurements on certain benchmark inputs. And finally, high level is proof of optimality, which we'll illustrate here with a square and multiply algorithm, because this kind of 4 steps constitute what can be considered as a meta loop, right? So if we've designed an algorithm, analyze the algorithm, and if that algorithm is optimal, then your job is done. However, if the algorithm is not optimal, then start again from square 2, design a different algorithm, hopefully more efficient, analyze it, and try to prove optimality of that. And we're going to illustrate that principle with several examples. For example, 4 algorithms for Fibonacci numbers will be discussed, and these 4 algorithms also illustrate the impact of which primitive operations are permitted. Remember, we talked about primitive operations for your strategy to graduate from high school, which could be high-level operations like graduate from middle school, graduate from university, or they could be small-scale operations like getting up in the morning, entering the bus, and so on. And similarly for algorithms, can be considered using or combined using either large high-level operations or low-level operations, and of course, which operations you are permitted to use, what is the meaning, the semantics of these operations, and what is the cost of every single operation. Is every operation has the same cost, the same running time or memory, or do they have different costs? That all affects the overall performance of your algorithm and must be reflected in its theoretical analysis as a prediction of its later practical performance. So we'll illustrate that with 4 algorithms computing Fibonacci number. Then we'll have a recap of mathematical recurrences, which all occur in the analysis of recursive algorithms, and their asymptotic solution according to the master theorem, which hopefully you have learned about or are encouraged to look up from your discrete mathematics class. We will apply these recurrences and their asymptotic solutions to various algorithms solving polynomial multiplication. So here again, we're going to look at several algorithms, not just one, a sequence of algorithms of improved asymptotic efficiency, first log multiplication, then Karatsuba multiplication, two multiplication, and an entire family of operation algorithms from the PhD thesis of Stephen Cook, the P versus NP problem Turing Award winner. And we'll close this chapter 1 with an example of matrix multiplication where again there's a sequence of algorithms with increasing efficiency, but no known optimality. So actually some people conjecture that there's always a better algorithm, even asymptotically better, and that the optimum cannot be reached, but also nobody knows where that optimum could even be located asymptotically. So that's our plan for this chapter 1, and let's start with talking about the power of abstraction. So let me start with a small anecdote. Namely, when I was in high school, I was enjoying computer programming, and my ambition was to write the fastest sorting program ever. So I sat down and uh, uh, look up into the assembly code, because assembly code gives you most control over the CPU. Intel 86 assembly code, and I counted the cycles of every single operation and removed one cycle, thus resulting in a faster program in the innermost loop of my sorting program. And thus, at the end, I was really convinced I had written the fastest sorting program. However, later when I entered university and learned about the algorithm, I realized what I had implemented was bubble sort, a highly optimized version hand-tuned to Intel processor, but bubble sort. And you probably know that bubble sort is not a very efficient sorting algorithm asymptotically. So I had fallen into the trap of that Donald Knuth had warned about. Premature optimization is the root of all evil, or put differently, I had failed to see the big picture of algorithm, and I had got lost in the small scale picture of assembly code. And so this is where I fell into the trap and failed to use the power of abstraction. And let me illustrate that further by reminding you of how our computer is actually composed of. So here you see a picture of the world's first transistor, and transistor's operation. I mean, the invention of the transistor is a is of course a big breakthrough, but understanding transistors operation requires advanced quantum mechanics. It's a semiconductor, so there are electrons in bands, and they can move up and down in the band depending on. So it's basically baseline is it's really advanced quantum physics required to understand a transistor. But do you understand the transistor? Maybe you don't, and you don't need to. That's a sense of abstraction, because what you really need to know is, for example, here transistor put into a case, and even further, the abstract transistor as a control switch. So when there's a signal entering at the base, then the signal from the uh, 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 input can proceed to the output. So it's a control switch, and that's already an example of abstraction, because in this level, everybody can understand transistor as a controlled switch for passing digital signals. Moreover, on a higher level, combining these transistors to realize more complex functionality in this way is very maybe confusing and hard to understand what is happening here. And that's why we can abstract from these soldering details and just look at the circuit diagram. So here you see transistors combined into Boolean gates, ternary gates in this example, and AND gate, OR gate, and so yes, here and here. And in this picture, it becomes much more transparent. On this abstract view, it becomes much more transparent what all these transistors combined are going to realize, namely kind of a Boolean function based on the theory of George Boole. Now, combining such Boolean circuits into one single integrated circuit is the next level of abstraction. Then combining such integrated circuits into a more powerful functionality, such as arithmetic logical unit on a board, and then even more abstract, putting all these things together into a central processing unit, which is in turn part of a motherboard with memory, and all these things constitute a computer hardware, but well, we don't need to know all these details anymore, because yeah, nowadays everybody can use computers, which is maybe a achievement of Steve Jobs. Before, computers were could only be used by experts, but nowadays it's everyday object of use based on all the abstraction, hiding all the details from quantum physics and soldering and combining integrated circuits to yield a certain functionality, on which then the next layer of abstraction software builds on, like the basic input-output system and various device drivers for graphics unit or hard disk or network connectors. Again, this built on computer hardware without needing to know the details of computer hardware, because the BIOS is kind of the interface layer. So again, next layer of abstraction is the operating system, which in turn builds on device drivers. So if we proceed to a different computer hardware, we only need to replace the BIOS and device drivers and can use the same operating system, on top of which then there's the library of object um, uh, code, and on top of that there's high-level programming languages. So this is a huge hierarchy of layers of abstraction, and the benefit is that we can ignore and thus focus on the big picture, or we can also look at details, for example, moving to a different hardware from the PC, for example, to a laptop, which is entirely different hardware, but still yeah, using a different BIOSes. The same operating system can be installed on different hardware, so kind of being able to replace different hardwares without affecting the higher levels. That's the power of abstraction. For example, we could also replace operating systems. We could use these operating systems to write a programming high-level Java programming language, or we could use this operating system, or we could use this operating system. So that's arguably even the purpose of Java, right? To be able to write code for not only for different computer hardware, but even higher up the hierarchy of abstraction, also for different operating systems. So to summarize, abstraction gives a tremendous power by enabling to focus on the important aspects and deliberately ignore details that can be neglected, such as, for example, my focus on assembly code, clock cycles. That's where I really failed to look and miss the big picture, the high-level picture of algorithm design. And so that's about the power of abstraction. We can ignore all the underlying details until down to the quantum physics of transistors, and that's what we will do in this course. However, occasionally one also needs to look more closely into lower levels. For example, the first large-scale distributed computer using a bunch of interconnected Apple machines turned out that it would kind of fail like once a day, and closer inspection turned out that this was because some radioactive particle would hit occasionally some memory bit and flip a transistor. So that's when people had to start developing error correcting memories. But that's also an example where ignoring the low levels of abstraction um, um, or only looking at the low levels of abstraction allowed to understand the cause of this problem. Of course, in high level of abstraction, memory is considered, reliable, and no effects of quantum physics are considered. Um, so we'll also see such examples in our algorithm design, depending on where we first look at the large scale picture only, and then realize we need to look more carefully also at some lower levels of abstraction to get an accurate and realistic prediction of the performance, for example, of our algorithm. So power of abstraction. And now we move on to talk about the virtues of computer science. And again, I'm going to illustrate that with examples and anecdotes. So here you see a picture of Ada Lovelace. Ada Lovelace is arguably the first programmer. She had to kind of write programs for the analytical machine devised by Charles Babbage. So here's a picture of her, but the virtues is what really makes the difference between computer science and electrical engineering. It seems that many people nowadays don't really are not aware of this difference. And to be fair, in many departments, EE departments and CS departments, the topics pursued by research group are basically the same in both departments. So is the boundary, the difference really has been has um, can become blurred. So let me take the opportunity to remind you, and the difference between electrical engineering and computer science is arguably the very same difference that generally applies to between engineering and science, right? So in science, we're interested in the why things work and how they work and whether they are optimal. So it's a fundamental perspective and a rigorous formal perspective, while in engineering, one is happy when something works at all, right? So as soon as, for example, consider the example of a refrigerator, right? So designing and manufacturing refrigerators is, for example, topic in engineering, right? On the other hand, knowing how a refrigerator works, why it works, that requires understanding of thermodynamics. Thermodynamics being a part of physics and thus a part of science. And designing optimal refrigerators, refrigerators that use, for example, the least amount of external energy, that's described by Carnot processes according to the second law of thermodynamics. That's a question pursued in science as opposed to engineering. And similarly, in computing, when you have a running system, then that's good from the perspective of electrical engineering. But a question like, is this system provably reliable? Is it provably optimal? These are questions pursued in computer science. And to this end, we need to start with a formal rigorous problem specification. Which computational problem is to be solved at all? And we're going to look at examples and non-examples in just a minute. The next step is algorithm design as opposed to start coding, which is what I the trap I fell in when starting to write assembly code and skipping the process of designing sorting algorithm at all. It just took what is known as bubble sort, took that for granted. So, and in algorithm design, we need to first agree on which primitives are allowed to be used to combine the bigger functionality. What is the meaning, the semantics of these primitives, and what is the cost of each primitive? Cost could, for example, include mostly its running time, but it also could involve cost measures such as memory consumption or communication volume. And then analyze that algorithm theoretically as opposed to empirical measurements, analyze the correctness, make sure that it satisfies and complies with the problem specification, analyze the overall combined cost of all the operations and loops asymptotically. This is different from, for example, empirically running the coded program on various example inputs using timing measurements in seconds or hours. Because if you run the same program on a different computer, or if you run the same program on a different input, then it could behave entirely differently, whereas the asymptotic analysis and correctness is kind of a universal property of the algorithm that is independent of the input, depends only on the input size, for example, and independent on the specific computer hardware, which is in agreement with our perspective of abstraction. And after having analyzed the algorithm you've designed, look at whether it's optimal. If you can prove it optimal, then your job is done and you can go on home or proceed to a different problem. If it's not optimal, then start over from square two, design another algorithm, analyze the other algorithm, and hopefully be able to prove that optimal. Or you have to start over again a third time. So what you see here is already kind of a meta loop, and we're going to see examples of such a meta loop, namely sequences of algorithms that are more and more efficient until finally we hit, or we never do hit, the optimal algorithm. So these are the virtues of computer science. And now I'd like to illustrate the importance of problem specification as the first virtue of computer science with some examples and non-examples, counterexample. So in many cases, I find that many students are not aware of the importance of specification or even of the notion of specification. So let me give you some non-example. Consider the problem of finding a good friend or a good spouse. This is a non-example of a specification because everybody has a different perspective of what constitutes a good friend or a good spouse. So if somebody claims to have come up with a solution to the problem of finding a good friend or spouse, then most likely somebody else will not consider that a solution at all. So that here, this problem lacks uniqueness. There's ambiguity of what is considered a solution to this problem. And so this is a non-example of a specification. Similarly, for the problem of deciding which movie should we watch maybe later. Again, this is a highly ambiguous specification and thus not a good specification. Specification does not need to be formal. Formal specification is one possible way of achieving unambiguity and uniqueness, but it's not the only way. As long as all parties involved agree and there's no confusion left, then that's good enough, a specification. However, if there is a confusion maybe between your your contractor and you're asked to write a program for a certain problem. It's a common kind of joke in software engineering that the biggest problem in software engineering is not in computer or engineering problem, but a psychological problem, finding out what the user wants. The user does not know what the user wants. So arriving at a problem specification that also the user understands and accepts, that's a huge endeavor in real-world software engineering projects. And often there's actually later turns out to be a disagreement or a misunderstanding, and then sometimes the two parties end up in court and need court to decide whether the program you have written and sold is according to the contract provided by the contractor deal with your boss or supervisor. Here's another more subtle non-example of specification. How many angels can dance on the head of a pin? That's a famous or infamous musing in philosophy. So there's no clear answer to that problem. How many prime number twins are there? That's a famous problem in number theory. And so there's a unique answer to that problem, yes or no. But here the non-specification aspect is more subtle. Maybe how can you convince somebody else that your answer is correct? That means finding a proof to that, to your claim. And that is a huge open problem. People believe that there are infinitely many prime numbers, but nobody is able to prove that. Here's a more logical non-example, interesting intellectually. Is no the only correct answer to this question? This looks like a decision problem where the possible answer is yes or no. Either one of them, like in the previous example about the infinite number of prime twins. But if you look more closely and think about it, let's suppose that the answer to this question is yes. Then it means that no. Let's first suppose that the answer is no. Then that means that no is not the only correct answer to this question, right? That means that also yes is a correct answer to this question. But if yes is the only correct answer to this question, then that means that no is not the only correct answer to this question. So either way, if you suppose that the answer to this question is yes, or that the answer to this question is no, you arrive at a contradiction. This is an example of a paradoxical question, which provably has no consistent answer. So this is something from logic, actually. And similar, another paradoxical question from logic based on Berry's paradox is the question: what is the smallest positive integer that cannot be described in English using 100 characters? So also this superficially looks like a unique mathematical specification. There always exists least positive integer, but semantically this leads to contradiction. So the gist of this slide is specification is important. It may, but doesn't have to be formal, but it has to be well specified. Make sure that the problem has an answer and that the answer is unique. So that's about specification. Moving on from specification to algorithm design as opposed to coding, I told you my own anecdote about devising a hand-optimized sorting program in assembly code. Here you see such an example of assembly code in Intel 32-bit assembly code, and but you don't really see what is happening here, right? So this is too low a level in our hierarchy of abstraction. Assembly code is too close to hardware to really see what's happening to use the power of abstraction. On the other end, here's a too high level of abstraction. I mean, here we simply call the sorting method of the data type arrays without knowing how that method is actually implemented, how it works, and also without knowing how fast it is, for example, and how much memory it uses. For example, it looks like it's only one instruction, right? One call to the sorting method, but we all know that the sorting method in your standard library uses different amount of time depending on the size of the array, for example, maybe also depending on the data in the array. So this is too high a level of abstraction in our hierarchy on the right hand. The left hand side of assembly code is too low a level of abstraction. So what we aim at in algorithm design is a suitable, and I'm going to say more about that in a minute, a suitable level of abstraction where on the one hand one retains the overall picture, but it is also at the same time has control over the correctness and efficiency to yield a prediction for the actual performance prior to implementation and independent of which hardware it is implemented on and what data it is run on one benchmark or another. So that's the benefit of algorithm design as opposed to coding. So when we proceed with algorithm design, well, the first thing we should agree on after having settled the specification is which primitive operations are permitted in order to solve that computational problem. Are we supposed to solve it using assembly code or machine instructions? Are we operating on that low level of abstraction, or are we supposed to use high level, such as pre-implemented methods of data types to so that's something to be agreed upon, and so that's kind of a meta part before starting to even devise algorithms. Also, the semantics of these operations has to be clarified in advance. For example, when we operate on integers, here the add instruction here, as we can see, operates not on mathematical integers, but on hardware integers, which have here 32 bits length, which means there's a wraparound happening after adding 2 to the 32 minus 1 and incrementing then that at the next step it's not 2 to the 32 but it's 0 wraparound, which is different from the semantics of adding or incrementing on mathematical integers provided, for example, by Java big integer. So the semantics of the add instruction has to be clarified, otherwise we produce algorithms that are erroneous, right? So semantics and which primitive operations are we allowed to use? Addition, or are we allowed to use sorting as a high-level method? And what is the cost of these operations? So as I said, superficially, this call to the Java sorting method looks like one instruction, but its running time and memory consumption is not just one. It depends on various aspects, such as the size of the array and the data stored in the array. So for realistic prediction of an algorithm, we need to have a realistic model of the cost of each primitive operation used by that algorithm. The assembly code example, for example, add instruction here uses 2 cycles, let's say, whereas a more complicated instruction like integer division can use maybe 100 or 200 cycles. So in order to get a realistic prediction of a assembly code, we also need to, and that's what I did when I was focusing to lower level of abstraction, counting and adding cycles to get a prediction of the actual program. How do we describe algorithms as opposed to codes? One way, but only one possible way, is to use pseudocode. Pseudocode is a kind of an intermediate level of describing algorithms between the high-level picture and the low-level picture of assembly code. Here you see a pseudocode of the bubble sort algorithm, where we can really see what is happening. So this seems like a good trade-off between too detailed and too abstract. We can see here there are two loops nested, and we see how often each loop is iterated, and thus we can also analyze the number of operations performed by this pseudocode. What we do not see here is yet how much every single operation costs. For example, here's this assignment or this swap operation may be counted as one operation, or maybe analyzed more carefully. It depends on the size of the data being swapped here. So pseudocode, but we're also going to encounter other ways of describing algorithms other than pseudocode. And all these are methods that allow us to kind of trade off between the high-level abstraction, the overall picture, and low-level, where we can get a more hands-on and more detailed view of the computer details. Maybe in some cases we might even want to or need to go as low as the hardware level, taking into account, for example, such as modern CPUs performing speculative execution and branch prediction that affect the performance of modern CPUs, and that also were the source of vulnerabilities and security problems. So having ignored that low level, that's what made people forget about these vulnerabilities, and only later they started to become exploited, and thus people realized that it is not always possible to simply ignore the lower levels. And this all the purpose is to not fall, as I did, into the trap of premature optimization, which already Donald Knuth warned about. So that concludes our first part of chapter 1, introduction. To recall, we've talked about the levels of abstraction in general and in computing, and we talked about the virtues of computer science, and we've given examples of the importance of the first virtue, problem specification, and non-examples for that, and the second virtue, algorithm design, as opposed to coding. And next, we're going to look at the importance of algorithm analysis and depending on which primitive operations with various semantics and costs are permitted. So stay tuned for that. So let me now illustrate the impact of having different primitive operations and the impact of the different semantics of primitive operations and the impact of different costs of primitive operations in the design and the question and the analysis and the question of optimality of an algorithm. And we'll do that here with a very simple example, namely the example of integer multiplication, and later we'll look at more sophisticated example, namely the example of Fibonacci number calculation. So here the problem specification is to multiply two n-bit integers, right? And on the highest level of abstraction, maybe this is just one single operation provided by your high-level programming language, just a multiply operation. But this counting this as one operation yields an inaccurate and prediction of the actual performance, as you can imagine, right? Because naturally multiplying longer integers takes more time than multiplying short integers. So at least the dependence on the length parameter n should be taken into account. And also we should express the high-level operation of multiplication as a sequence of lower or at least middle level operations. And let's just for now take these middle level operations to be additions. So now the goal is to devise an algorithm to multiply two n-bit integers using the sequence of addition. So that's the primitive operations that we have now agreed on. And the semantics of these primitive operations is just mathematical addition. And so let's agree on that we're going to ignore wraparounds effect or just suppose that the computer, that's a hypothesis that the underlying hardware data type is sufficient in order to add two integers, n-bit integers without wraparound. Then there's a very naive algorithmic solution to this multiplication problem. Then we take the maybe the first integer a and multiply it to itself b times, where b is the second n-bit integers. Here you see b expressed as a sequence of bits of length n. So maybe that's what elementary school kids would do, repeatedly add a to itself b times. So that means that is an algorithm for integer multiplication written as a sequence of integer additions, namely as b integer additions, where b is the value of the second integer to be multiplied. Or we can also switch roles, of course, using commutativity. But the point is here, the number of additions, that is the runtime of this abstract algorithm, depends on the value of the integer b, but we want it to depend only on the length n of the integer b. And there's a possible huge discrepancy between the length and the value. If you think about it, an input integer can have value up to 2 to the n minus 1, which is exponential in n. So there's a possible exponential difference in depending on the length of the integer and depending on the value of the integer. For differently, we want an algorithm which is efficient with respect to its dependence on the length. And you also already know this algorithm, the grade school multiplication or long multiplication, it's called. Let me write down copies of the first integer a shifted by one bit more each, and then add those copies where the corresponding bit in the second argument b is non-zero, is 1, right? So let's say b0 is 0, then replace this shifted copy of a with 0, replace this shifted copy of a with 0, and keep only those shifted copies of a where the corresponding bit in b is a 1, and then add all these. So that means our new algorithm is again a sequence of additions, but now it's only at most n additions, namely at most one addition of a shifted copy of a corresponding to the at most n digits of 1 occurring in the second argument b. So that is our better algorithm, because now its running time, the number of operations is only linear in n rather than exponential in n, and linear in the value of b. And we've expressed integer multiplication as a sequence of n additions under the hypothesis that every addition has costs one operation. So that's the cost hypothesis, and there are no wraparounds. That's our second hypothesis on the semantics of the primitive operations addition. But again, as you know, this is an unrealistic prediction of the actual performance, because we cannot simply count the number of additions. The cost of an addition more realistically will depend on the size, the length of the integers to be added, right? So to get a more realistic analysis and prediction of this grade school multiplication, we need to take into account that the integers we are adding n times each have at most so in order to get a more realistic prediction on the actual performance, we need to step down one level in our hierarchy of abstraction and recall that at the end of the day, what your computer actually operates on are bits, right? Transistors, and processing 1 bit each, or maybe bytes. But I'm going to talk about the difference between bits and bytes in a second. So for now, let's have a closer look at the algorithmic cost incurred by this algorithm by refining our hypothesis that the cost of each addition, originally we counted only the number of additions, thus supposing that every addition has cost 1 or unit cost, uniform cost. And let's refine that by now supposing that adding two n-bit integers costs roughly O of n bit operations. So now we'll analyze this algorithm from the bit cost perspective, which is more involved, but also more realistic from the perspective of actual computing. And then this is easy in this example. We have n additions, and each addition involves integers of n bit, or at most 2 n bit actually each, so that a more realistic prediction in the bit cost model says that the bit cost is quadratic n squared bit operations. So basically, it's the same algorithm as before, but now analyzed with a different semantics, with a bit different cost for each addition, variable cost, namely depending on the length of the integers being added. Or put differently, we can also consider this as an algorithm which not only operates, uses only addition, but uses bit operations like AND or, you know, that integer addition can be expressed using a sequence of binary ANDs and ORs. This is called a half adder and full adder, and by concatenating full adders, one arrives at an integer adder. So this is a different way of looking at our algorithm, using not integer addition as primitive operation with variable costs, but equivalently looking at this as an algorithm using bit operations with unit costs. Now every single bit operation is supposed to have the same cost. And thus, this algorithm from both perspectives yields a quadratic running time. And let me now take a small detour regarding the question of optimality, because if you think about it, this algorithm, the input to this problem consists of two n-bit integers, so it has binary length 2 n-bit, and also the output has 2 n-bit length. So That's kind of the best one can hope for. Any algorithm must at least read the input and must at least produce the output. So at least n or 2n bit operations are required for reading, at least 2n bit operations are required for outputting. And what happens in between, that's of course depends on the algorithm under consideration. But our algorithms here using quadratically many bit operations, that seems like a inefficient, right? So the input is kind of linear length, the output is linear length in the number of bits. Only the intermediate calculations quadratic. And this raises the question, is there a better way of multiplying two n-bit integers in terms of the bit cost? And indeed, there is. The first such algorithm has been maybe described by Kawatsuba and Toom and Cook. We will return to this algorithm when we look at the similar but subtly different problem of polynomial multiplication. But the world record for this problem is held, I think, by Harvey and Joris van der Hoeven from 2020, who designed an algorithm that uses only n log n bit operations asymptotically. So this is really close to the information theoretic optimum of needing at least n bit operations for reading the input and n bit operations for printing the output. So there's only a kind of overhead of factor log n for the intermediate calculation. So this is an example of an advanced algorithm for multiplying two n-bit integers. Yes, so that being said, let's now move on to emphasize the importance of asymptotic optimality of algorithms. Right, as I've repeatedly mentioned in computer science, as opposed to electrical engineering, we're not interested in absolute running times, but we're interested in asymptotic running times. And the reason is that having an asymptotically more efficient algorithm easily trumps any improvement in asymptotic acceleration, maybe like proceeding to a faster computer or even proceeding to a array parallel computer. And let me illustrate that with this table. On this table, you see 5 columns, each column corresponding to a different hypothetical computer. At the rightmost column, you see a computer running at a gigahertz clock rate, namely with nanosecond for each operation, order of nanosecond. The next second column from the right refers to a megahertz computer that is using roughly a millisecond for each operation. This is example, the Apple IIe or the Commodore 64, where computers running at a megahertz rate, whereas nowadays computers use the gigahertz, as you see in the rightmost column. The third column from the right is refers to a computer running at a frequency of kilohertz, so 1,000 operations per second. Then the next one is using a hypothetical computer performing 1 operation per second. And just for reference, recall that Konrad Zuse's Z3 computer, the first universal digital computer, actually could perform like roughly 9 operations per second. So this one here in the second column from the left is really hypothetical. And the next one, the rightmost column, is even more hypothetical. A computer able to perform 1 operation every 10 seconds only. Very, very slow computer. But this hypothetical table for illustrating purposes, these different speed computers are executing different algorithms with different asymptotic performance. So the slowest computer here is operating an algorithm with asymptotically logarithmic running time. The next faster computing is running an asymptotically slower algorithms with n log n running time, like the record algorithm by Hauger and van der Heuvel I just mentioned. The next faster computer is running an even slower asymptotic algorithm with quadratic running time, this one with cubic, and this one with exponential running time. So you really see this is a trade-off, right, between fast computer and slow algorithms on the one hand, and slow computer and fast algorithms on the other hand. And for small inputs, it's really the speed of the computer that determines the outcome of this race. The fastest computer beats all other, but it already um, is on par with the second fastest algorithm running a polynomial time algorithm. And this comparison becomes even more striking as the input size increases. So, for example, input size 100, even the fastest computer running an exponential time algorithm will never terminate. It will take 40 billion years to terminate. We'll call that our universe is something like 13 billion years old. And so, whereas the slow computers have no problem, of course, they run asymptotically efficient algorithms. And when the input size increases, then that benefit becomes even more striking, where the slowest computer easily outperforms all others because it runs an asymptotically logarithmic running time algorithm. So that just the message to take away here is focus on asymptotic efficient algorithm. And that's also from a cost perspective very cheap, right? You can simply upload a more efficient software without any investment in hardware. And only once you have found and the asymptotically optimal algorithm, which we call this the vast virtue of computer science, asymptotically optimal algorithm, then it makes sense to start optimizing, to maybe purchase a faster computer or maybe even a parallel computer. But first, the largest gain in performance is obtained by proceeding to an asymptotically more efficient algorithm, which is why and what we're focusing on in this course, asymptotic and algorithm analysis, as opposed to empirical program running time measurements. These are this year, the empirical running time measurements are a common way of comparing programs in, for example, using benchmark suites, but it's common that one algorithm is more faster, maybe a factor of 2 on one benchmark suite, and the other one is faster on the other benchmark suite. So it's really hard, if not impossible, to compare two programs using empirical and using asymptotic running times, whereas using asymptotic analysis, one obtains a universal measure of performance of algorithms that allows to rigorously compare different algorithms in their asymptotic growth, and that can then, of course, be tailored to the specific computational setting by taking into account the clock rate, for example, or the specific data size to be processed. So the lesson here is asymptotic performance provides a concise and universal information about algorithm performance and predictions that are realistic and reliable. So that being said, let's now move on and recall some example classes of asymptotic growth in Lando's Big O notation. And the point in asymptotic analysis, I'm not going to repeat the formal mathematical definition here. Please refer to your class in discrete mathematics for that purpose. The purpose of an asymptotic analysis is on the one hand, to simplify the performance expressions, right? So asymptotic analysis, we ignore, on the one hand, we ignore constant factors. So this means that, for example, 17 times n squared is the same as 2 times n squared asymptotically, and also it ignores lower degrees contributions, such as 5 times n plus 8 times log n. All these are neglectable and are neglected in asymptotic growth notation, thus arriving at much simpler expression for runtimes. And also the other aspect being ignored is small small sizes. So here you see that in this picture, for small inputs of length less than k, actually the blue algorithm is faster, but is slower, but asymptotically it's faster than this algorithm. And that's what is important in asymptotic analysis. Here you see some example classes of asymptotic growth: constant asymptotic growth like 17, logarithmic asymptotic growth like a square root, linear growth, quasi-linear growth, n log n or n log squared n, quadratic growth, n squared, cubic growth, n cubed, polynomial growth, n to the c for some constant exponent, where the value of the exponent is again ignored according to a paradigm of abstraction. Superpolynomial growth means that the exponent may depend mildly on the parameter n, like logarithmically. Exponential growth means that the exponent grows linearly or even superlinearly in the parameter. Doubly exponential growth and tetrahedration means that it grows corresponding to a tower of height n of exponents. So these are worse and worse to asymptotic running time. So we're going to hope and aim for polynomial, and then going to refine to cubic, quadratic, or n log n, corresponding to us climbing down the hierarchy of abstraction from high-level polynomial, and then only start to optimize following the Laclau's paradigm. So that's levels of asymptotic growth, and here you see corresponding diagrams. So n factorial grows like n to the n, then we have exponential growth 2 to the n, and so on until down to logarithmic and constant growth. And between any of these two classes, there's also a class in between. So this is by far not exhaustive. There are many more classes of asymptotic growth, just to give you a picture. I would also like to repeat the emphasis on not confusing the binary length and the unary length, which is basically the value. I emphasize that when we had our first two algorithms for integer multiplication, the first one would repeatedly add a times the value of b, which had a number of additions corresponding to the value of a, and then we refined that to grade school multiplication, where the number of additions was depending on the length of a. And to illustrate that the important distinction, consider writing this integer 2 to the 999. And I use the capital N to denote that this is a large integer, on the one hand in binary and on the other hand in unary. In binary, the length of that is roughly 1000 bits, and 1000 being basically the value of the integer. The logarithm of the value is basically the binary length. On the other hand, the unary length is basically the same as the value. So the difference between length and binary length and unary length is a difference between logarithmic and exponential. So it makes a huge difference. So please make sure not to confuse that when people write usually small n as the complexity parameter. Please make sure what is meant with small n. Usually it's the binary length, but sometimes it's not. For example, deciding whether an integer is a prime number using the sieve of Eratosthenes proceeds by testing all possible prime divisors up to value square root of n. Of course, if there's none found up to value square root of n, then we can be sure that there is no prime factor at all, right? Because otherwise there would be a complementary prime factor. So this means it takes a number of operations which is roughly the square root of n, but n is the value of the argument here, right? So this looks like it's in sub-polynomial, sublinear, but it is sublinear in the value, not in the binary length. Whereas in terms of the binary length, which is the logarithm, this scheme of Eratosthenes has exponential running time, and the polynomial time algorithm, polynomial in the binary length, actually binary length raised to the 6th power, was devised in 2002. This is the problem of deciding whether a given integer is a prime number. The problem of factoring a given integer, on the other hand, still up to nowadays is not known to have a polynomial time algorithm, an algorithm polynomial in the binary length. But of course, there are many algorithms polynomial in the value, but that's not really helpful. And as a matter of fact, people are so convinced that there is no such factoring algorithm polynomial in the binary length. That is, this is the basis that the RSA crypto system is built upon, which you probably use all the time, for example, in online banking. So please refrain from confusing binary length and unary length. Okay, so that concludes our first three virtues of computer science, and I'm now going to proceed to the last virtue, the virtue of optimality. And to this end, I would like to also give a first example of our meta algorithm for algorithm design and for abstraction and abstract specification. So the problem I want to consider in order to illustrate the quest of optimality is a powering problem. The powering problem, we fix some monoid. So if you don't know what a monoid is, that's a mathematical structure that allows for multiplication. And multiplication is an operation. So this covers, again, following a paradigm of abstraction, this covers many examples. For example, integers can be multiplied, or matrices can be multiplied, polynomials can be multiplied. Anything that can be multiplied forms a monoid. It doesn't even need to be commutative, but anyway, so my point is, this is a very general hypothesis that you have something that can be multiplied. And the powering problem is the following: given an element from this monoid, an integer or matrix or whatever, and raise that to the nth power, where n is arbitrary but fixed. Okay, and how are you supposed to solve that algorithmic problem? Well, it's well specified, right? We can repeatedly multiply x using the operation, so the primitive you are allowed to use in this problem is multiplications only. So even if we're talking about polynomials here, which can also be added, refrain from using addition, only use multiplication, and even since we're abstracting, ignore that this is polynomial, only consider that these elements x can be multiplied. And the goal is to use as few multiplications as possible, counting only the number of multiplications, ignoring, again, by abstraction, whether different multiplications take different time depending on whatever. So this is a first abstract view, and later actually we will refine that analysis to specific monoids like integers or matrices, and obtain more realistic predictions and more realistic algorithm. But for now, let's stick to that first high-level abstract view and consider our first algorithm, which repeatedly multiplies x to itself. So from this perspective, it means we multiply things n minus 1 times, n or n minus 1 makes no really difference asymptotically. So that's the first kind of algorithm. But following our meta paradigm, let's look at whether we can do better than n minus 1 multiplications. And to this end, we're going to look at another algorithm, a recursive one. So this recursive algorithm, I'm going to refrain from even stating the pseudocode, but just simply write down mathematical formula. In case n is even, then n over 2 is an integer, and we can kind of recursively raise x to the n over the second power, and then take the result and multiply that result to itself. So squared here means multiply to itself. Whereas in case n is odd, then n minus 1 is even, and we can divide it by 2. And we have to, and again, square, but now we need to kind of perform an additional multiplication by x to kind of correct for the, that we have rounded down here to the next smaller even integer. So these are just mathematical expressions, but you can easily, and I want you to turn it into pseudocode for training purposes. Let me refrain from doing that. Instead, let's move on to analyze this recursive algorithm in terms of the number of multiplications used. And since this is a recursive algorithm, its analysis becomes a recurrence described here. Namely, if n is even, then we use t of n over 2 multiplications by induction hypothesis for the recursive call, plus 1 multiplication for the squaring, which means simply multiply the result to itself. So we don't make 2 recursive calls and then multiply, but of course we only make 1 recursive call, store the result of that call, and then multiply it to itself. In the odd case, we have this additional multiplication by x, as you can see here, resulting in the plus 2 in the recursive analysis. Also, observe that I took the liberty of simplifying this expression n over 2 in both cases with n over 2 rounded down. So you can easily see that the odd case is the one dominating the cost. So we can solve that recurrence easily. So when we want to raise it to the first power, we don't need any multiplication at all, right? And in general, we have this recurrence, even in the first case, the odd case, and we can solve that, for example, by induction, and see that this means the overall number of multiplications is at most 2 times the binary logarithm of n. I leave that to you. That's just mathematics, so please go ahead doing that. Which means now we have found an asymptotically better algorithm. The first algorithm used both n multiplications, the second one uses all log n multiplications. So, so that means now we're asked again with the question, is this algorithm asymptotically optimal or not? And we're going to prove, and that's the last we're going to do today, we're going to prove that it is optimal. And to this end, we use some mathematics, simple lemma that will prove that our algorithm with 2 times logarithmic multiplications is asymptotically optimal up to this factor of 2. We're going to prove that any algorithm that follows these constraints of using only multiplication and counting the number of multiplications will need to do form at least logarithmically many multiplications, so that in particular our algorithm is optimal. And then, in essence, the importance here is really being able to argue about any possible algorithm subject to these rules using only multiplication and counting the rules. This is something extremely powerful. How can you argue about any algorithm, even one that has not yet been conceived or considered, arguing about all possible algorithms. And you see how we're going to do that using mathematics, using the first observation, item A of the lemma. Any algorithm following this paradigm of starting with input x and using only multiplications produces only monomials in x as intermediate results and thus also as final results. So it can, for example, not produce polynomials because it's not allowed to use additions. It cannot produce inverse monomials because it's not allowed to use division. So this statement is easy to prove by mathematical induction whenever the algorithm after a certain sequence of operations has produced a collection of intermediate results and then in the next step chooses two of these intermediate results to multiply with each other, then the result will again be a monomial, right? Monomials of the least class of anyway, so that's obvious. And the second claim or observation is that after L multiplications, all intermediate results, which are monomials by item A, must have degree at most 2 to the L. So degree at most 2 to the L. That's again easy to see by mathematical induction, namely after L multiplications, induction hypothesis is induction start is obvious, but induction hypothesis and then in the induction step, the algorithm will take two intermediate results having degree at most 2 to the L each, multiplying them will result in a new, possibly new intermediate result of degree at most 2 to the L plus 1, that's the induction step. And now putting all both claims together, we see that any algorithm, that's important, requires at least logarithm of n many multiplications, which follows by simply taking the logarithm of both sides of this inequality, respecting that logarithm is monotonic. So, and this proves that any algorithm requires at least log n multiplications. Our algorithm suffices with 2 times log n multiplication. So up to this constant factor, our algorithm is optimal and we can stop looking for better algorithms, or we can now finally start optimizing on lower levels, try to optimize the factor maybe, or we can look more closely at the data type we are multiplying, refining the hypothesis that every multiplication takes one operation, taking into account maybe the size of the data to be multiplied, which in our later examples are going to be integers or matrices, where of course the size of the integer, the matrix, matters to get a more realistic prediction of the actual running time. But we're going, this is a very kind of a helpful meta algorithm which we're going to use. The next part where we're going to devise algorithms for computing Fibonacci numbers. So that's all for today, and I'm going to close and by recalling that we've talked about the importance of abstraction, and we've talked about the four virtues that arguably distinguish computer science from electrical engineering, similarly to science being different from engineering, namely first problem specification, where we talked about examples and non-examples. Second, algorithm design as opposed to coding. Third, algorithm analysis and correctness as opposed to empirical runtime measurements. And finally, optimality of an algorithm, as we saw here, or if the algorithm is not optimal yet, then start over again. And the final thing I want to emphasize here is the importance of the primitives allowed here. Here we only considered multiplications as the permitted primitives, but if we also consider, for example, logarithm and exponentiation, then this powering problem can be solved using a constant number of operations, but much more powerful operations than simply multiplication, namely also using exponentiation and logarithm. So what is considered an optimal algorithm really depends on which primitive operations can be used and what is the cost of the primitive operation. So thank you very much. And finally, I'd like to answer questions from the chat. Thank you very much. So one student asked, which programming language does our course refer to or build on? And that's a very good question. I'm very happy to elaborate on that because, well, based on our principle of abstraction, the answer should be doesn't matter. All our considerations should, are, and will be independent of the programming language under consideration, whether it's Java or Python or C++. On the other hand, you're supposed, you're encouraged to implement the various algorithms in order to actually experience the benefit of asymptotic improvement. So I want you to implement an exponential time algorithm and to get annoyed at how terribly slow it is. Then with that, being motivated to implement a perhaps more involved algorithm, spend the effort of implementing a more complicated algorithm and enjoy the benefit of improved running time and maybe even do that again. And we're going to do that in the next session when we talk about Fibonacci number, and we're going to repeat that again when we talk about polynomial multiplication. So that being said, thank you very much for your attention and see you next time.